Welcome to the Sleepy Cosmos channel, a place where science and serenity meet. Here we explore the quiet wonders of the universe, from dark matter to string theory, all told in a calm, soothing rhythm designed to help you relax, drift, and dream among the stars. Each video is a guided journey through the cosmos, slow, meditative, and filled with real science wrapped in gentle storytelling. So if you love space, curiosity, and the peaceful side of knowledge, you're in the right place. Make sure to subscribe for more new sleep narrations every week. And if you'd like to reach out for collaborations or business inquiries, you can contact us at the sleepycosmoschannel@gmail.com. Now, settle in, take a deep breath, and let's drift into the universe together. Black holes, the quiet monsters that shape the universe. Let your breath settle gently, let your thoughts soften, and allow your attention to drift toward a quieter place within you. A place where the universe moves slowly, where gravity whispers instead of pulls, and where the deepest mysteries of spacetime unfold with a calm, patient grace. Tonight, we step into the quiet presence of black holes, not as threats, not as monsters of destruction, but as silent architects of the cosmos, entities that guide the motion of stars, shape the structure of galaxies, and influence the evolution of the universe with a stillness that feels almost meditative. As you rest here, settling deeper into comfort, imagine the universe not as a chaotic expanse, but as a vast, rhythmic fabric, a continuum gently curved by matter and energy, responding to gravity the way a calm lake responds to a drifting breeze. A black hole is simply a region where this fabric curves so deeply, so smoothly, that even light must follow its inward flow, not because it is forced, but because geometry itself guides it there. This journey tonight is not about urgency, not about solving mysteries, not about racing toward answers, but about resting inside the questions, letting them surround you like soft cosmic air, letting curiosity drift lightly, without pressure, without expectation. Black holes, despite their reputation, are among the most peaceful objects in the universe. Quiet, predictable, elegant. They do not reach out to pull things in. They simply shape the space around them, and objects, following the natural curvature of space-time, move where the geometry guides them. A calm, inevitable, gentle flow. As you breathe, feel that same natural flow within your body, a slow rhythm, a steady settling. In the vastness of the universe, black holes form not through violence, but through transformation. A massive star, after a long life of fusion and radiance, reaches a point where it can shine no longer, and gravity, which has always been present, quietly takes over, guiding the star inward, compressing its core, shaping a new region of space-time. A black hole, a quiet monument to the mass that once burned brightly. This transformation is serene when viewed through the lens of physics, a smooth shift in equilibrium, a moment where gravity becomes the dominant storyteller, and space-time responds accordingly. As you listen, allow these ideas to move gently through your awareness, not as concepts to memorize, but as waves to drift upon, soft, steady, unhurried. Black holes reshape the flow of time itself, causing moments to stretch slowly near their boundaries, allowing seconds to linger, allowing the universe to breathe more deeply in their presence. Imagine standing at a distance, watching a clock near a black hole, its hands moving more slowly, its rhythm lengthening, not broken, not stopped, simply eased into a different tempo, a cosmic slowing that mirrors the relaxation you feel now. This dilation of time is not dangerous, it is not harmful, it is simply the natural response of the universe to the curvature of gravity. Everything in nature adjusts calmly, flowing according to geometry, flowing according to mass, flowing according to the quiet rules that guide the cosmos. When you think of a black hole, let go of the image of a swirling, violent storm, and instead picture a smooth, deep well in the fabric of reality, a gentle basin toward which light and matter drift, not in fear, but in accordance with the simplest and most elegant laws of physics. As you breathe, feel yourself drifting into that same smoothness, that same soft gravity pulling your thoughts inward, toward stillness, toward rest. Black holes also anchor galaxies, providing a central mass around which billions of stars orbit, their gravity offering stability, their presence helping to define the structure of the cosmos. In a way, every galaxy carries a quiet heart, a central object that shapes its motion, not loudly, not violently, but with the silent authority of gravity, an authority that arises from mass alone, from the curvature of spacetime, from the calm rules that govern every corner of the universe. As your body settles further, you can imagine yourself drifting at the edge of one of these immense structures, watching stars circle slowly, feeling the deep, steady pull of the central black hole, a presence both powerful and peaceful, like the slow, constant rhythm of your breath. The darkness surrounding a black hole is not an emptiness. It is simply a region where light cannot climb outward, a place where the inward flow of spacetime is too deep to escape, a place defined by geometry, not by danger. Even the event horizon, often imagined as a catastrophic boundary, is simply a threshold where paths bend inward, where light follows the natural curve of spacetime, where nothing special happens locally, where an observer falling through would feel no sudden shift, just a continuation, a smooth passage, a deepening of the gravitational landscape. Tonight, as you listen, as your thoughts slow, as your breathing softens, you can imagine that same smooth passage in your mind. A gentle transition from wakefulness into rest, from thought into quiet, from the bright surface of your day into the soft darkness of sleep. Black holes teach us that darkness is not an end, but a transformation, a change in the way space and time behave, a region where our usual intuitions fade, and a deeper, more elegant order takes over. They remind us that not everything bright is strong, and not everything dark is dangerous. In the universe, light and darkness dance together, guided by gravity, shaped by space-time, woven into structures far larger and calmer than anything in daily life. As the introduction draws you further inward, let yourself rest in this idea that the universe is vast, predictable, and patient. Nothing rushes, nothing hurries. Everything follows smooth, mathematical curves. Everything unfolds across billions of years. Everything flows. And you, in this moment, can flow with it, breathing gently, thinking softly, allowing the quiet presence of black holes to guide you into deeper stillness, into the calm gravity of sleep. When you let your mind drift into the quiet around a black hole, you begin to understand that darkness is not a presence. It is an absence of escape, a gentle boundary shaped by gravity rather than light. Darkness here is not sinister, not violent, not hungry, but simply the natural result of space-time curving so deeply, so smoothly, that even photons follow paths inward, not because they are forced, but because the geometry of the universe leaves them no other route. This darkness is calm, predictable, a region defined not by chaos, but by the elegance of physics working exactly as it should. Let your breath settle into that idea, a kind of cosmic simplicity, where the deepest shadow in the universe is nothing more than the graceful bending of space and time. Around a black hole, light does not vanish abruptly. It stretches, bends, lingers, moving along curved geodesics that arc toward the event horizon, paths carved by gravity's quiet influence. You can imagine beams of light traveling near this region, their trajectories gently pulled inward, their wavelengths stretched, their colors softened toward red, a cosmic sigh as energy disperses across distance, a visual whisper of gravity's power. This bending of light, called gravitational lensing, creates one of the most serene phenomena in astrophysics, a halo, a ring, a smooth distortion of the background universe, revealing the shape of space-time itself. It is as though the universe paints a soft outline around the black hole, showing where geometry dips into a deeper well, where gravity becomes the quiet sculptor of light. As your thoughts drift, imagine floating near such a place, not close enough to fall, but near enough to see the fabric of space curve gently downward, like the surface of a calm lake being pulled into a slow whirl, smooth, quiet, inevitable. Darkness becomes a gradient here, not a wall, but a transition, from regions where light can escape to regions where paths bend inward beyond retrieval. This transition is marked by the event horizon, a boundary famous in name but misunderstood in nature. The event horizon is not a physical surface, not a barrier, not a membrane you would feel, but a geometric threshold, a location where all possible future paths point inward. If you drifted across it, nothing would push against you, nothing would change abruptly, your motion would remain smooth, your experience continuous. Locally, physics behaves just as it does anywhere else, because the laws that govern the universe do not break at the horizon. they simply express themselves in a different frame. What makes the event horizon special is not the sensation of crossing it, but the information it prevents from leaving. The way it hides regions of spacetime behind a perfect curtain of geometry. From the outside, an object approaching the horizon appears to slow, its signals stretched, its light red-shifted until it fades into darkness, a gentle dimming, a gradual quieting, as though the universe is whispering the object into shadow. But from the object's own frame, motion continues, unaffected, smooth and uninterrupted, falling deeper into the curvature without resistance. Following gravity's natural script, this dual perspective, the outside view and the infalling view, is one of the most profound features of black holes, a reminder that reality is shaped by the observer, that time and space are not fixed, but fluid, responsive, woven into a fabric that changes with motion and mass. Let your mind rest in this fluidity. Imagine space-time not as rigid architecture, but as a responsive medium, a soft, four-dimensional surface that bends gently, curving around mass, settling into valleys and wells where gravity becomes strongest. A black hole is simply the deepest of these wells, a location where curvature becomes so steep, so deep, that paths converge inward forever. Even here, nothing is violent at the boundary. The geometry is continuous, smooth, differentiable, guided by Einstein's equations as predictably as any orbit or wave. This smoothness is what makes black holes so paradoxically peaceful. Despite the intensity of their gravitational pull, the structure around them remains stable, calm, mathematically clean. The darkness you see is not a swirl of chaos, but a region where no light returns, a consequence of deep curvature, not a symptom of violence. Imagine watching a distant star drift behind this region, its light bending around the black hole, forming arcs, rings, soft distortions that wrap around the shadow. A gravitational dance where geometry choreographs every movement. These lensed images reveal something beautiful, that even in darkness, the universe finds ways to illuminate structure, to show the curvature of spacetime through light that bends yet survives, offering glimpses of the gravitational landscape. If you floated near this scene, you would feel no sudden force, only the steady pull of gravity. The same pull you would feel near any massive object, just stronger. Because the mass is concentrated in a smaller region, there is no cosmic wind here, no turbulence, no roaring sound, only the silence of space, the steady curvature of geometry, and the infinite patience of gravity. As your attention softens, imagine drifting slowly around the black hole, tracing the curvature with your thoughts, feeling the gravitational stillness as a kind of cosmic calm. This stillness arises from symmetry, from the spherical shape of spacetime around non-rotating black holes, from the smooth solutions of general relativity that describe their form, from the way geometry organizes itself naturally around mass. Even rotating black holes, with their twisted spacetime, maintain a kind of graceful structure, an axis of spin, a dragging of inertial frames, a gentle swirl built into the fabric of reality. Light near such an object spirals, follows warped paths, clings to the curvature, painting arcs that reveal the rotation not through sound or motion, but through the direction light chooses to travel. As you drift deeper into this idea, let yourself feel the calm in these motions, the predictability, the mathematical serenity. Black holes may be extreme, but they are also the most perfect expressions of gravity. Solutions where the equations become pure, simple, elegant. That is what makes their darkness quiet, not empty, but orderly. A place where spacetime reveals its deepest curvature, its smoothest descent, its calmest inevitability. Even near the edge of a black hole, particles move along precise paths, orbits remain stable until they reach specific radii, and the geometry guides everything with unwavering consistency. This region, called the photon sphere, is where light can orbit the black hole, circling endlessly if perturbed just right. A delicate balance between inward pull and tangential motion, a cosmic tightrope woven from the rules of spacetime. These orbits are unstable. A slight disturbance sends photons either inward, toward the horizon, or outward, back into the universe. But the very existence of such orbits reveals the subtlety of gravity here, its richness, its complexity wrapped inside calm curvature. As you breathe, you can picture this sphere as a soft boundary of looping light, a shimmering ring suspended around the darkness, a region where photons hesitate, pause, linger before choosing their path. Everything near a black hole behaves in this patient, measured way, governed not by chaos but by geometry, by the slow flow of spacetime, by the deep well carved by mass. This is the true quiet nature of darkness, not an abyss, but a structure, a shape, a gravitational form sculpted by the universe with mathematical precision. Feel yourself drifting with this structure, following the curvature with your thoughts, letting the darkness soften into calm understanding, letting the smoothness of spacetime guide you deeper into rest, deeper into curiosity, deeper into quiet. As you continue drifting through the quiet geometry around a black hole, the darkness becomes something more than an absence of light. It becomes a map of curvature, a silent diagram drawn into the structure of spacetime itself. When physicists describe this region, they do not speak of chaos. They speak of metrics, curves, coordinates that fold inward with mathematical precision, revealing how mass shapes the universe without sound, without motion, without any need for force. This calmness is easiest to feel when imagining spacetime as a smooth fabric, not a literal sheet, but a conceptual surface that responds gently to mass, dipping, curving, settling into wells that guide all motion within them. The deeper the well, the stronger the curvature, and a black hole represents the deepest curvature allowed by the equations of relativity, a place where the geometry becomes so steep that all possible paths slope inward, a region where the flow of spacetime itself leans toward the center. But even with such depth, the curvature at the boundary remains smooth, a gradual steepening rather than a sudden cliff, a continuation of the same geometry that shapes planets, stars, and galaxies. Everything is the same, just intensified, pure, distilled. The darkness around a black hole is the shadow of this curvature, not a thing in itself, but the shape of spacetime made visible by the way it redirects light, bending it, stretching it, guiding it around the gravitational well. This bending creates an optical illusion, a luminous ring around the shadow, a boundary where photons skim along the edge of gravity's deepest descent, orbiting briefly before deciding whether to escape or fall inward. These photon orbits form a delicate region, one where light neither commits to leaving nor staying, a place balanced on the razor-thin edge of spacetime's curve. As you let this idea settle, you can imagine photons gliding around the black hole, following their geodesics, their natural paths, circling the darkness like faint echoes of the stars behind them. In this region, light behaves in ways that are profoundly counterintuitive, yet profoundly calm, revealing how gravity shapes everything, even something as swift and weightless as light. And this bending of light does more than create beauty. It reveals the structure of darkness itself, the silhouette of the event horizon, the invisible boundary beyond which no signal can return, emerging not through direct observation, but through the absence of escaping photons. The event horizon stands as a quiet divider, not a physical surface, not a wall, but a mathematical place, where spacetime curves so steeply inward that all paths lead further down. Nothing marks its presence except the behavior of light, and the way time stretches near it, slowing, elongating, making every signal fade into deeper red, until even that final wavelength slips below visibility. From a distance, this gives the horizon a soft appearance, a smooth darkness, a shadow that glows around its edges, outlined by the photons that orbit and bend around it. If you drift closer in imagination, not falling, just observing, you begin to feel the stillness of the region, the way spacetime seems to stretch, the way time itself flows differently, not broken, not halted, but slowed in a natural, graceful way. This slowing of time near strong gravitational fields comes directly from relativity, the idea that time's flow depends on the shape of spacetime, on the gravitational potential, on the depth of the curvature around mass. Near a black hole, these effects intensify, but they remain smooth, predictable, following the same equations that describe the orbit of planets, the motion of satellites, the bending of starlight. Everything is continuous, differentiable, elegant. Even the experience of falling toward a black hole would be calm. Contrary to popular imagery, you would not be torn apart instantly, not at the horizon, not in the region around it. Instead, you would feel normal forces, normal sensations, nothing abrupt, nothing violent. The horizon is gentle, a place where local physics behaves exactly as it always does, because the laws of nature do not recognize the horizon as special. only distant observers do. Those who see time stretch and light fade, those who watch signals slow until they vanish. This difference in perception is one of the quiet wonders of general relativity, the realization that reality shifts depending on perspective, that time and space are not universal, but personal, shaped by motion, shaped by gravity, shaped by the curvature of the path you travel. Let yourself rest in that thought, that the universe is not rigid, but flexible, patient, willing to allow different observers to experience different slices of reality, all correct, all consistent with the deeper geometry. As you drift a little deeper into the idea of darkness around a black hole, you might imagine how matter behaves near such a place. Dust clouds, stellar winds, particles drifting slowly inward, following spirals shaped by gravity and angular momentum. Even their descent is not chaotic, it is orderly. A natural flow guided by the geometry of spacetime, a soft spiral that gradually narrows, tightening into cleaner orbits, until the final approach becomes inevitable. In these motions, you can see the power of curvature, not as a force pushing, but as a landscape guiding, a contour of spacetime that matter simply follows, the same way rivers follow the shape of valleys, the same way planets follow the curvature around stars. The darkness simply marks the region where these paths no longer lead outward, where the inward slope becomes too deep for return. But the slope itself is smooth, graceful, mathematically precise. Imagine tracing this slope with your thoughts, moving softly down the curvature, feeling the inward pull not as a threat, but as the natural direction of the landscape, a gravitational valley carved by mass, quiet, deep, patient. This is what makes the nature of darkness around a black hole so calming. It is not a chaotic void, not an unpredictable abyss, but a stable feature of the universe, a place where the laws of physics reveal their deepest clarity, their cleanest solutions, their quietest beauty. Even the stillness has structure, subtle layers of curvature, regions where light hesitates, paths where time stretches, places where matter spirals with gentle inevitability. The boundary between light and shadow becomes a gradient, a soft fall-off, a smooth transition from illuminated space to the dark region where photons cannot climb. This gradient is visible in simulations, in observational images, in the patterns of lensed starlight, all showing that darkness here is not abrupt, not sharp, but shaped by the curvature of space-time. As your awareness softens, you may feel that gradient inside yourself, the gradual transition from wakefulness into rest, from clarity into drifting thought, from the bright surface of attention into deeper quiet. Black holes mirror that transition, guiding energy inward, guiding light inward, guiding time inward, in a slow, steady, gravitational descent. This descent is the essence of their nature, the quiet nature of darkness, a region defined not by fear but by geometry, not by violence but by curvature, not by chaos but by the smooth, inevitable, patient rules of gravity. Let your thoughts drift a little more deeply now, following the curve, feeling the quiet, resting in the softness of the universe's darkest, yet most peaceful regions. As you continue drifting through the quiet landscape near a black hole, the darkness reveals even more layers of structure, subtleties born from the way spacetime curves, each one a soft expression of gravity's deepest geometry. If you imagine yourself floating far from any turbulence, in the calm vacuum surrounding the black hole, you would see the universe distorted in gentle, sweeping ways, stars stretched into arcs, background galaxies elongated, light bending around the curvature in smooth ribbons. This bending is not a trick of vision, it is the true path that light must follow, a path written by the geometry of spacetime, the same geometry that controls the orbits of planets, the flow of time, the behavior of everything that moves. Near a black hole, this geometry becomes a kind of soft funnel, a deepening of the cosmic landscape, a place where the inward curve grows steeper, yet remains perfectly smooth, devoid of edges, devoid of breaks, a continuous descent into gravity's most focused form. The stillness here is profound, so much so that even the idea of direction changes. What seems like inward or outward becomes relative, dependent on the paths available in spacetime, paths that narrow gently, like a valley leading toward a river, inevitable, predictable, quiet. This soft inevitability defines the event horizon, a boundary not of matter, but of futures. A place where all possible timelines slope inward, not by force, but but because the structure of spacetime leaves no outward roots. If you picture spacetime as a flowing river, the horizon is where the current becomes too swift to swim against. Yet locally, the water remains smooth, clear, gentle. This analogy helps reveal something essential, that the horizon is not a place of violence, but a place where the inward flow of spacetime surpasses the speed at which light can move outward. Light itself tries to climb, but the river of spacetime flows inward faster, carrying it down, guiding it deeper, softly removing all outward paths. To an outside observer, anything approaching the horizon appears to slow, signals arriving more stretched, fainter, redder, a cosmic quieting, as though the universe is dimming the falling object into silence. This effect is called gravitational redshift, and it arises naturally from the stretching of time near deep curvature, a stretching that becomes infinite at the horizon, pushing outgoing signals toward longer wavelengths until they vanish beyond visibility. But to the object itself, time remains normal, unbroken, smooth, a reminder that the horizon is not a physical barrier, just a change in the structure of space-time that separates observers. These dual perspectives, so different yet both correct, illustrate the strange beauty of general relativity, the way it allows different observers to describe different realities, all consistent with the same underlying geometry. As you rest into these ideas, you might imagine drifting even closer, hovering near the photon sphere, the delicate region where light can orbit the black hole, circling endlessly if placed just right, a perfect balance between speed and curvature. This orbit is unstable. A slight push sends the photon away, either into the darkness or back out into the universe. But the existence of this orbit, this delicate ring, reveals the richness of the gravitational environment, a level of structure that emerges only in the deepest wells of spacetime. From here, you would see the universe distorted almost beyond recognition, the sky curved around the shadow, light streaming in from behind you, forming rings and arcs that wrap across your field of vision. The black hole would not look like a disk, but like a sphere swallowing the center of sight, surrounded by a halo of bent starlight, a luminous outline shaped entirely by gravity. This outline is sometimes called the photon ring, or more poetically, the last ring of light, a place where photons have circled many times before escaping or falling inward. Its presence is subtle, but it carries with it deep information about the curvature of spacetime, the mass of the black hole, the spin, the precise shape of the event horizon. This quiet ring, barely visible yet profoundly important, is one of the keys to imaging black holes, a whisper of the geometry hidden beneath darkness. As you imagine this scene, you may sense how calm it feels, even in such an extreme environment. Everything follows rules, everything moves along defined geodesics, everything behaves exactly as the mathematics predicts. There is no chaos, no unpredictability, only gravity shaping the universe with perfect consistency. Matter that drifts near the horizon but does not fall inward follows spirals that gradually tighten, their motion slowed by the curvature, their paths guided by the geometry, their descent smooth, inevitable. And yet, at a comfortable distance, the gravitational influence is gentle, no different from any other massive object, because gravity weakens with distance, and black holes obey the same inverse square law as stars and planets. If our sun were somehow replaced by a black hole of the same mass, Earth's orbit would remain unchanged, a quiet demonstration that black holes do not devour indiscriminately. They simply shape spacetime in a concentrated way. This understanding softens the fear that surrounds these objects, revealing them not as cosmic predators, but as natural expressions of gravity, solutions to Einstein's equations, places where curvature reaches its deepest form. As your awareness drifts further inward, you may imagine the gravitational field not as a pull, but as the contour of a landscape, a valley drawing matter toward its lowest point. A smooth gradient of curvature, guided by mass, guided by symmetry, guided by the rules that govern all matter. These rules create the stillness around a black hole, a stillness arising from the absence of outward paths, not the presence of violence. The silence becomes the defining feature, a silence made of trapped light, a silence shaped by geometry, a silence where even time flows differently, stretched, lengthened, softened by gravity. This silence is the true nature of darkness around a black hole, not emptiness, not destruction, but a calm region where space-time has curved too deeply for light to escape, a place where the universe hides its interior behind a veil of geometry. As you breathe softly, you can feel that geometry, not physically, but conceptually, a widening understanding of how mass shapes space, how curvature shapes motion, how darkness itself is structured and precise. This marks the completion of the quiet journey through the nature of darkness, the bending of light, the calmness of the event horizon, and the still geometry surrounding a black hole. And now, with this layer of understanding settled gently in your awareness, the narrative begins its slow drift into the next theme, the quiet sculpting power of gravity itself, how it shapes orbits, how it guides motion, how it forms the cosmic architecture we see across the night sky. Gravity reveals itself most clearly when imagined not as an invisible pull, but as the quiet reshaping of space-time, a gentle curvature that guides the motion of everything that drifts within it. As your attention softens, imagine space not as an empty stage, but as a flexible four-dimensional landscape, a surface that bends around mass, producing valleys and slopes that objects naturally follow. This idea, the essence of general relativity, allows gravity to be understood not as force, but as geometry, smooth, continuous, patient. A black hole is simply the deepest expression of this geometry, a region where space-time curves downward so far, so gracefully, that all paths lead inward, like the lowest point in a vast cosmic valley. But the curvature does not begin abruptly. It builds slowly, softly, from far away, subtle enough that planets and stars follow gentle orbits, never sensing the true depth that lies at the center. If you picture yourself far from the black hole, floating in the calm vacuum around it, gravity would feel familiar, weak, almost gentle, indistinguishable from the pull of any massive star. But as you drift inward, curvature deepens, not suddenly, but gradually, your path gently bending, your trajectory adjusting, as though guided by an unseen hand made only of geometry. This bending defines every orbit, every path taken by matter or light, every slow circle traced by stars near the center of galaxies, all following the contours that mass has carved into spacetime. It is this quiet sculpting that forms the architecture of the cosmos, from the elegant ellipses of planets to the spirals of galaxies to the whirling disks of gas around black holes, all of it shaped by gravity's silent hand, a hand made of curvature, not force. Let your thoughts drift with this idea, imagining space itself as a soft surface, responsive to mass, warped by its presence, curving ever so slightly beneath every object. Every star leaves a depression, every planet creates a valley, every black hole carves the deepest well of all, a well so steep that even light cannot climb its slope. Yet the slopes remain smooth, the curvature continuous, differentiable at every point, a testament to the quiet elegance of Einstein's equations. As you breathe slowly, imagine walking across a landscape shaped by gravity, feeling the contours beneath your feet, the slow descent toward regions of deeper curvature, not dangerous, just inevitable, the natural direction of spacetime's shape. This analogy helps reveal why objects fall, not because they are pulled, but because they follow the shortest path available, the geodesic, the curve that spacetime offers them, the path that requires the least resistance, the least energy, the least deviation. A black hole shapes these paths most profoundly, its curvature deepening sharply near the horizon, narrowing the possible routes, funneling all motion inward. Far from the black hole, the geodesics resemble familiar gravitational orbits, ellipses, circles, slow arcs traced by stars, each one sculpted by geometry. Stars near the center of galaxies, like the ones orbiting Sagittarius A, move in fast, tight ellipses. Their paths shaped not by the black hole reaching out to grab them, but by the structure of spacetime around them. A deep well created by mass, a landscape they simply follow. From this perspective, their motion becomes serene, not frantic, not chaotic, but smooth, guided, steady. Even the fastest stars, those whipping around the galactic center with incredible speeds, are simply following the contours of gravity, moving along the geodesics carved into spacetime, never forced, only guided. As you drift further into this understanding, picture how time itself changes near such curvature, slowing as gravity deepens, stretching the rhythm of reality, creating a different pace of existence near the black hole. This time dilation is not dramatic in most places, but near the horizon, it becomes profound. a reminder that gravity shapes not only space, but time as well, weaving the two together into a single unified fabric. Space curves, time stretches, and together they create the motion we see. The arcs of planets, the spirals of galaxies, the infall of matter near black holes, all of it the result of geometry, not force. Think of a marble rolling on a curved surface. The marble moves not because something pulls it, but because the shape beneath it guides its path, curving its motion, directing its trajectory, sculpting its orbit. This is the essence of gravity as a sculptor, the quiet shaping of motion through curvature. In the region around a black hole, this shaping becomes more intense, but just as smooth, just as continuous, just as elegant. Matter that enters these deep regions begins to follow tighter spirals, its path narrowing as curvature steepens, its motion tracing out the invisible structure of spacetime, not randomly, but with perfect mathematical compliance. As gas and dust approach, they form an accretion disk, a thin, spinning structure shaped by gravity and motion, not forced into chaos but arranged by physics into a stable, dynamic form. The inner regions of this disk move at incredible speeds, relativistic speeds, because spacetime there curves sharply, creating orbits that require immense velocity to remain stable. This motion is not violent, it is simply the natural consequence of geometry. Matter following the shapes carved into spacetime, moving faster where curvature is deeper, slower where curvature eases. Even the heating of the disk, the radiation it emits, the energetic processes that occur near the horizon, all arise from motion through curved spacetime, from particles interacting in a deep gravitational well. From the interplay of geometry and energy. At larger scales, gravity sculpts entire galaxies, organizing billions of stars into spirals, bars, clusters, each arrangement the result of mass shaping spacetime and spacetime shaping motion. The central black hole acts as an anchor, a point around which the galaxy stabilizes, not because it pulls, but because its mass defines the deepest curvature, setting the gravitational rhythm that the whole system follows. This rhythm permeates the galaxy, guiding star formation, shaping orbits, influencing the long-term evolution of stellar populations. Gravity sculpting becomes a cosmic choreography, a quiet dance of matter and spacetime, moving in sync with equations that describe the universe at its most elegant. As your awareness softens, you can imagine drifting through one of these galaxies, feeling the slow swirl of starlight, the gentle arcs of orbital motion, the gravitational contours flowing beneath everything, steady, predictable, calm. This is the universe shaped by gravity as a soft sculptor, a universe where motion arises not from force, but from geometry, not from chaos, but from curvature, not from violence, but from the smooth, mathematically precise shaping of spacetime. The journey through this understanding settles now into gentler depths, a natural pause, a quiet recognition of the elegance in the way gravity organizes the cosmos. And with that calm understanding, the narrative begins preparing to drift into the next theme, the gentle birth of black holes themselves, how stars collapse, how gravity takes over, how transformation, rather than destruction, creates the quiet giants that shape the universe. Gravity continues its quiet work in the region surrounding a black hole, softly sculpting spacetime, shaping the flow of motion, guiding every particle, every photon, every orbiting star. As you drift deeper into this understanding, you begin to sense that gravity here is not a force acting upon things, but the structure those things move through, a framework, a geometric field that defines all possible paths. Imagine a leaf drifting down a gentle stream. The leaf does not choose its direction, it simply follows the currents beneath it, currents shaped by the contours of the riverbed, by stone, by slope, by earth. Matter near a black hole behaves the same way, drifting along the currents of spacetime, guided not by push or pull, but by geometry, by the invisible contours carved by mass. The deeper the curvature becomes, the tighter the paths, the faster the motion, the more intense the relativistic effects. But even these intensities move with elegance, not with chaos, not with violence, but with the smooth inevitability of equations that do not break, do not falter, do not change their nature. This elegance becomes especially clear when imagining the orbits of stars near a supermassive black hole, stars completing full revolutions in mere years, moving at a significant fraction of the speed of light, yet never colliding, never being torn apart. simply tracing the curves that spacetime offers them. Their paths resemble elongated ellipses, each orbit slightly shifting due to relativity, precessing around the black hole, the orientation of the ellipse slowly rotating with each revolution, a gentle demonstration of how curvature modifies motion. This effect, known as relativistic precession, is silent, smooth, subtle, a quiet signature of gravity's deeper nature. As your awareness softens further, you can imagine drifting above these stars, watching their motion from a timeless vantage point, seeing how their paths form a dance, coordinated by the geometry of the space they inhabit. A dance not choreographed by external force, but by the shape of space-time itself. The closer matter moves to the black hole, the more striking the choreography becomes, especially near the innermost stable circular orbit, a threshold defined by relativity, a place where the curvature becomes too steep for stable motion. Inside this region, no circular paths exist, only spirals, inward, inevitable, guided by geometry. Even these spirals remain smooth, a calm descent, not an explosion, not a tearing, just the continuation of a curve that allows no outward turn. Gas falling inward forms a disk that gradually thins, its temperature rising from friction, from collisions, from magnetic turbulence. Yet the motion, the orbital structure, remains defined by spacetime's shape. This disk becomes one of the most luminous structures in the universe, a contradiction to the darkness of the black hole itself, light orbiting near shadow, energy rising near silence, a cosmic juxtaposition formed by gravity's sculpting. If you could drift above this disk, you would see spirals of glowing plasma, each particle speeding around the black hole, each orbit influenced by time dilation, each curve stretched by the depth of space-time. The inner regions of the disk glow brightest, heated by the tremendous velocities required to maintain temporary stability, velocities dictated not by choice, but by geometry, the only possible speeds that balance the inward pull of curvature. This glowing structure is not chaotic, it is intensely ordered, a dynamic equilibrium shaped entirely by physics, a cosmic sculpture in motion, each strand of light tracing the curve of space-time. Above and below this disk, magnetic fields twist and stretch, wound by rotation, funneling charged particles into narrow beams, relativistic jets that extend far into interstellar space, their motion near the black hole governed by frame dragging, the twisting of space-time around a rotating mass. Frame dragging itself is one of gravity's softest yet strangest effects, a phenomenon where rotation pulls space-time along with it, not violently, not abruptly, but gradually, smoothly, dragging everything nearby into a swirl, a cosmic eddy created by rotation. This effect forms the ergosphere, a region outside the event horizon where space-time is forced to rotate, not because matter pushes it, but because geometry itself is moving, twisting, carrying everything with it. Inside this region, no object can remain still relative to distant space, not a particle, not a photon, not even light traveling against the rotation, because space-time itself is rotating beneath it, carrying everything along. This dragging of space-time reveals gravity's sculpting power in motion, not just shaping paths, but shaping frames of reference, shaping the way time flows, shaping the way space behaves. Imagine drifting through the ergosphere, feeling the swirl beneath you, not as a force, but as a gentle shift in direction, a slow rotation of the entire structure of reality, carrying you with it. Everything moves together, everything flows, everything follows the shape of space-time. Even the formation of jets, those narrow, powerful beams of plasma, arises from this geometry, from magnetic fields twisted near the horizon, from charged particles accelerating along field lines, from the combination of rotation, curvature, and plasma dynamics. Yet even these jets, some stretching thousands of light years, are structured, steady, collimated by electric and magnetic forces. Guided by the space they travel through, they do not emerge from chaos, but from alignment, from the precise conditions created by a rotating black hole, from the interplay of geometry and magnetism. Gravity's sculpting extends far beyond the black hole itself, influencing stars many light years away, shaping the orbits of entire clusters, guiding the long-term evolution of galaxies. The central black hole does not dominate by force. It dominates by mass, by presence, by the deep curvature it creates at the center of its galaxy. This curvature stabilizes orbits, anchors spirals, guides motion, serves as a focal point for billions of stars, a quiet anchor that holds the structure together. Even though the black hole occupies only a tiny fraction of the galaxy's mass, its gravitational influence extends across vast distances, subtle, steady, essential. Without this central mass, galaxies would drift, their rotational structure weakened, their long-term stability uncertain. Gravity acts here as a cosmic architect, shaping structure through curvature, designing equilibrium through mass, maintaining balance through geometry. The quietness of this influence becomes most apparent when imagining the galaxy from above, a slow, spiraling form, stars drifting along curved paths, gas clouds moving gently through gravitational valleys, all of it held together by the soft sculpting of spacetime. As you rest within this imagery, you begin to sense why gravity feels like a gentle force. Even though it governs the largest structures in the universe, it works without sound, without contact, without pressure, simply by shaping the stage on which everything moves. This completes the journey through gravity as a sculptor, the quiet hand shaping galaxies, the steady curvature defining motion, the soft bending of space-time that guides everything from photons to stars. And now, the narrative prepares to drift into the next theme, the birth of black holes themselves, the transformation of massive stars into quiet gravitational wells, the gentle takeover of gravity when fusion fades, and the serene collapse that forms the universe's quietest giants. The birth of a black hole begins long before the collapse, long before the star reaches its final moment, long before gravity takes full control. It begins quietly, deep within the core of a massive star, where fusion has burned for millions of years, creating light, pressure, and the delicate balance that keeps the star stable. For most of its life, a star exists in equilibrium, gravity pulling inward, fusion pushing outward, a gentle tension, a continuous negotiation between inward curvature and outward energy. But even this balance is temporary, because fusion has limits. It can only continue as long as fuel remains, as long as lighter elements can be merged into heavier ones, releasing energy that resists gravitational collapse. As the star ages, the fusion chain progresses, hydrogen to helium, helium to carbon, carbon to oxygen, each stage shorter than the last, each producing less outward pressure. Eventually, iron forms in the core, a final step that marks the quiet turning point. Because fusing iron does not release energy, it consumes it, and the star can no longer support its own weight. Gravity, which has always been present, always patient, begins to take over. The core collapses inward, not explosively at first, but smoothly, quietly, as electrons are crushed into protons, protons into neutrons, neutrons into an incredibly dense state. This collapse happens in fractions of a second, yet the physics remains continuous, a deepening of curvature, a surrender to gravity's simplest form. If the collapsing core is below a certain mass, it stabilizes as a neutron star, a dense object where neutron degeneracy pressure halts further collapse, allowing gravity and quantum mechanics to coexist in fragile balance. But if the mass exceeds that limit, there is no force in known physics that can resist gravity's inward pull, and the collapse continues, deeper, tighter, accelerating toward a point of no return. The formation of a black hole is not an explosion, it is a continuation, a smooth transition from one state of matter to another, from star to singularity, from radiance to silence. The outer layers of the star may be blown away in a supernova, a brilliant moment marking the end of fusion, but the core, the heart of the star, shrinks past every barrier, every pressure, every resistance. Gravity folds space-time inward, shaping the event horizon around the collapsing mass, a boundary that forms when the curvature becomes too deep for light to escape. Inside this boundary, the collapse continues, unseen, shielded behind geometry, falling endlessly toward a region where our equations reach their limit. This process, while extreme in energy and scale, remains guided by predictable physics, a serene and inevitable flow toward deeper curvature, toward the creation of a black hole. Let your awareness drift into this transformation, not as destruction, but as metamorphosis, the universe reshaping mass into a new form, a gravitational object defined not by what it emits, but by what it prevents from leaving. Stellar black holes form from these massive stars, their birth marked by collapse, their presence revealed through the curvature they create, curvature that shapes nearby motion, affects the paths of stars, and influences the evolution of entire regions of space. But black holes also form on far larger scales, through the merging of stellar remnants, through the slow accretion of matter, or perhaps through processes in the early universe, where conditions allowed primordial black holes to arise, tiny at first, but capable of growing over cosmic time. Supermassive black holes dwell in the centers of galaxies, with masses millions or billions of times larger than the Sun. Yet their formation remains one of astronomy's deepest mysteries. They may grow from the seeds of massive stars, or from dense clouds collapsing directly into black holes, or from chains of mergers between smaller black holes, each event a quiet deepening of curvature, a strengthening of the gravitational well at the galactic center. Despite their size, their birth shares the same fundamental process: gravity overcoming pressure, curvature overwhelming structure, the inward flow of spacetime becoming too steep for escape. As your thoughts soften, you can imagine how these giants grow, gently, steadily, drawing in stars that wander too close, absorbing gas clouds over millions of years, feeding on the slow drift of matter through the galaxy. Their growth is not constant, not ravenous, but episodic, dependent on the distribution of matter, the motion of stellar populations, the dynamics of galactic evolution. Sometimes they brighten. Surrounded by luminous accretion disks, their feeding visible across billions of light years, their jets piercing through interstellar space, a quiet beacon of gravitational power. And sometimes they rest, dark, undisturbed, a sleeping presence at the heart of the galaxy, shaping orbits without emitting light, influencing structure without revealing their form. Primordial black holes, if they exist, may have formed moments after the universe began, not from stars, but from fluctuations in density, small regions collapsing directly under their own gravity, creating tiny black holes with masses far below those formed by stars. These primordial remnants could still drift through the cosmos today, silent, invisible, their mass too small to reveal through accretion, yet still curving spacetime, still contributing to the gravitational fabric. Some theories suggest they might account for part of dark matter, their tiny gravitational wells sprinkled across the universe, each one a microscopic expression of curvature. Others propose that they could evaporate over time, shrinking through Hawking radiation, dissolving slowly into faint whispers of energy, a process so gradual that even small primordial holes would survive for billions of years. This variety in formation, stellar, supermassive, primordial, reveals the versatility of gravity, its ability to shape matter into extreme forms under the right conditions, its ability to create objects defined not by what they emit, but by the curvature they impose. As your mind drifts deeper into this idea, you begin to sense that black holes are not exotic in the way we often imagine. They are natural outcomes of gravitational physics, the endpoints of massive stars, the anchors of galaxies, the quiet products of density and collapse. Their births, though dramatic in energy, are conceptually simple: gravity exceeding pressure, curvature exceeding support, structure giving way to geometry. The moment the event horizon forms, a black hole is born, and the universe gains a new region where spacetime flows inward, a new well in the gravitational landscape, a new quiet sculptor of motion. Even after formation, the black hole continues to evolve, not through internal processes, but through external motion, through the matter that drifts too close, through mergers with other compact objects, through the slow accumulation of mass over cosmic time. Each new addition deepens the curvature, expands the event horizon, strengthens the gravitational presence. A black hole does not age the way stars do. It simply grows, becoming a deeper well, a more pronounced distortion of spacetime, a larger influence on its surroundings. And yet, even the largest black holes remain serene, silent, patient, their nature unchanged by scale, their structure governed by the same elegant equations, the same inevitability of curvature. This completes the gentle journey through the birth of black holes, their formation through stellar collapse, their growth into supermassive giants, their possible origins in the earliest moments of the cosmos. And now, your awareness drifts toward another quiet mystery: what lies beyond the event horizon, and how the interior of a black hole reveals both the strength and the limits of our understanding of gravity. As you drift deeper into the quiet story of a black hole's birth, the transformation becomes clearer: a slow surrender of structure, a peaceful yielding of a star's internal balance, and the gentle takeover of gravity as the final sculptor. After the collapse forms the event horizon, the new black hole enters a long era of stillness, an object defined not by change, but by the geometry it imposes on the universe, a presence silent in every wavelength. Except for the ways it bends light, shapes orbits, and influences the cosmic landscape around it. But the story of birth does not end at formation. It continues through the evolution of the black hole's mass, its interactions, its mergers, its slow and steady growth. Imagine a lone stellar black hole drifting through interstellar space, moving without hurry, its gravitational well subtle but persistent, its presence known only through the distortion of background starlight. A faint lensing effect that reveals its hidden mass. If a cloud of gas passes nearby, the gas does not fall in all at once. It spirals, guided by angular momentum, forming temporary arcs, streams, and ribbons of matter that gradually lose energy, slowly settling into tighter and tighter orbits. This accretion process is gentle in its earliest stages, a faint warming of gas, a soft glow invisible to most telescopes, a quiet reminder that black holes grow not through violence, but through the patient pull of curvature. As matter falls inward, gravity converts its potential energy into heat, radiation, and motion, creating luminous regions around the black hole, regions shaped not by the hole itself, but by the behavior of matter near the event horizon. These glowing disks are some of the brightest objects in the universe, contrasting sharply with the darkness beneath them, a cosmic balance between silence and radiance, between shadow and fire. This duality reflects the essence of black hole birth, a collapse into darkness surrounded by the glowing remnants of what once was, light circling shadow, energy spiraling around gravity's deepest well. And yet, even this brightness is fleeting. For once matter crosses the horizon, its story disappears from the observable universe, leaving behind only the deepened curvature, the expanded event horizon, the quiet growth of the black hole's mass. Over cosmic time, black holes may merge with others, their horizons touching, melding, forming a single larger gravitational well, a union marked by the emission of gravitational waves, ripples in spacetime that travel outward at the speed of light, carrying with them the memory of the merger. These waves are gentle, despite their scale, tiny distortions of spacetime, stretching and squeezing space as they pass, revealing the motion of massive bodies far across the universe, revealing the quiet collisions of black holes lost to darkness. Mergers are one of the ways black holes grow, each one adding mass, each one carving a deeper curve into spacetime, each one strengthening the gravitational shape left behind. Supermassive black holes form through similar processes, but on far grander scales, fed by the slow drift of gas within galaxies, by the collisions of stars, by the merging of smaller black holes over billions of years. These giants anchor the centers of galaxies, their growth intertwined with galactic evolution, their presence essential to the structure of spirals, ellipticals, and the vast clusters that populate cosmic space. Even as they grow, their nature remains simple, their properties defined by only three quantities: mass, spin, and charge, a remarkable reduction of complexity, a reminder that collapse simplifies, it does not complicate. This simplicity is known as the no-hair theorem, the idea that black holes have no additional features, no internal structure visible from the outside, no imprint of the matter that formed them, only mass, spin, and charge shaping the geometry of spacetime. The birth of a black hole erases details, leaving behind a pure gravitational object, a smooth curvature, a region of deep geometry where the universe's history is hidden, not destroyed, but concealed beneath the horizon. This concealment leads naturally into deeper questions, questions about what lies within, questions about singularities, about the limits of relativity, about the interior structure that remains hidden from the outside world. Inside the event horizon, the inward flow of spacetime becomes irresistible. Every path, every possibility, every future leads toward the central region, toward a point where the density becomes infinite in classical physics, a singularity, a place where equations fail, and our understanding reaches its edge. But this singularity is not a physical point in the conventional sense. It is a limit of our theories, a sign that relativity is incomplete, that a deeper understanding is needed, perhaps from quantum gravity, string theory, or some future framework. Even this uncertainty carries a kind of calm, a recognition that the universe holds mysteries beyond our current reach, that knowledge has boundaries, and that those boundaries can be places of curiosity rather than fear. Let your awareness drift into that unknown, not to solve it, but to rest in its presence, to accept that the interior of a black hole remains one of nature's quietest secrets, a place where gravity overwhelms our intuition, where space-time curves beyond our ability to describe it. This calm acceptance mirrors the serenity of collapse, the peaceful transition from star to black hole, the soft deepening of curvature, the emergence of a new gravitational well. The birth of a black hole is not a moment of destruction, but a shift in the universe's shape, a new configuration of space-time, a new presence in the cosmic landscape. And now, with this understanding settled gently in your thoughts, the journey drifts toward the next mystery, the question of what happens beyond the horizon, the inner flow of time, the geometry of the interior, and the calm silence that defines the unseen heart of a black hole. To imagine what happens beyond the event horizon, you must first allow your thoughts to loosen, to drift away from the familiar rules of space and time, and enter a region where intuition becomes quiet, where geometry becomes strange, and where the universe reshapes the meaning of direction, motion, and future. Crossing the event horizon is not marked by any sudden change, no boundary that feels solid, no sensation of passing through a barrier, because locally, physics behaves exactly as it does anywhere else, smooth, continuous, unchanged. The horizon is a global feature, a boundary defined by what cannot escape, not by what is felt, and an observer falling through it would continue smoothly, guided by the same geodesics that shape all motion in curved space-time. From the falling observer's perspective, nothing dramatic happens. The universe simply continues to flow inward, the curvature deepening, the paths narrowing, the future becoming a direction that points inevitably toward the center. Inside the horizon, every possible trajectory leads inward, not because of a force pushing you toward the center, but because the structure of spacetime tilts in that direction. The way time itself moves forward for you, the inward direction becomes the only possible forward in spacetime. This is one of the quietest yet most profound ideas in relativity, that inside a black hole, the inward direction becomes as unavoidable as the passing of time, a destination woven into the geometry of the universe. Let your awareness settle into that concept, the feeling of being carried by the fabric of reality, not torn, not crushed, but guided by the curvature that shapes the interior. Outside the horizon, you can move freely in space, choosing directions, adjusting your path, steering through the gravitational landscape. Inside, spatial freedom narrows. The directions available become limited. The geometry funnels all motion toward the singular center, a region where classical physics predicts infinite density, infinite curvature, the breakdown of the very equations that describe spacetime. Yet even this prediction carries a kind of calm, a recognition that our mathematical tools are incomplete, that the singularity is less a physical point and more a signal of the limits of our models, a signpost marking where new physics is needed. As you drift deeper inside the horizon in your imagination, the inward flow of spacetime becomes stronger, not in the sense of force, but in the sense of inevitability, the way a river gathers speed as it approaches a waterfall, even though the water itself remains smooth, continuous, unchanged. The curvature of spacetime increases, the slopes steepen, the inward direction becomes more sharply defined. Yet the experience remains calm. Gravity does not feel stronger locally, because free fall removes the experience of weight, leaving only the geometry guiding your motion. If the black hole is small, tidal forces become intense as you approach the center, stretching objects along one axis, compressing them along another, a result of the gradient in curvature, the difference in gravitational pull between nearby points. But for large black holes, supermassive ones, the tidal forces near the horizon are gentle, almost imperceptible, allowing an observer to fall deep inside before these gradients increase, allowing the descent to feel smooth, quiet, dreamlike. In either case, the geometry continues to carry you inward, toward the region where spacetime narrows, where the curvature approaches its extreme, where the classical description ends. Inside the horizon, space and time exchange roles in a way, not literally, but conceptually, because the inward direction becomes time-like, meaning it must be followed, while the directions that were once spatial become constrained, their freedom reduced by geometry. This inversion is one of the most elegant aspects of black hole interiors, a reminder that space-time is flexible, that time and space are not rigid categories, but ingredients the universe can mix, reshape, and reorder when mass becomes large enough. As your thoughts drift through this restructured space-time, you might imagine the radial coordinate behaving differently, no longer measuring distance, but serving as a measure of time until you reach the singular region. Each step inward marking the passing of moments, each deepening of curvature marking the flow toward an inevitable future. This future is the singularity in classical relativity, a place where geodesics end, where trajectories terminate, where the universe's geometry collapses into a point of infinite density. But modern physics suggests this picture is incomplete, that quantum effects may soften the singularity, create a new form of matter, or even prevent true collapse to an infinite point, replacing it with a transition, a bounce, a bridge, or a region described by unknown principles of quantum gravity. Let your awareness float in this uncertainty, a calm mystery, a region where science has not yet reached, a place where new ideas may emerge, where the structure of space-time could reveal something unexpected. Some theories propose that inside a black hole, space-time may continue into another region, a new universe, a separate branch of reality connected through the singular core, a possibility allowed by certain solutions to Einstein's equations, though not confirmed, and perhaps softened or altered by quantum effects. Others suggest that the interior contains a complex structure, a finite region where quantum gravity prevents the formation of a true singularity, creating a dense core of exotic matter, a place where space-time loops back on itself, or where information is stored in subtle quantum states. Each of these possibilities remains theoretical, resting at the boundary of our understanding, a gentle reminder that the universe is still teaching us, still revealing itself through equations, observations, and the quiet interplay between theory and mystery. While drifting through these ideas, it becomes clear that the interior of a black hole is not defined by violence, but by curvature, not by chaos, but by the quiet limits of our knowledge, a place where physics continues, but our tools falter. Even the singularity itself, despite its dramatic name, is not a physical object to be feared, but a placeholder, a mathematical signal telling us that the theory we rely on is incomplete, that general relativity cannot describe space-time at such extreme densities, and that quantum gravity must take over. This realization softens the singularity, removing the fear often attached to it, revealing it as an invitation to deeper understanding, a frontier, a question waiting patiently for an answer. As your mind floats in this quiet region, you begin to appreciate the interior not as a chaotic abyss, but as a domain of pure geometry, a realm defined by the inward flow of space-time, the narrowing of possibilities, the deepening of curvature, and the presence of a mystery that remains serene, gentle, calm. Eventually, all paths lead to the core, whether the singularity is a point, a loop, a quantum region, or something we have not yet imagined. The classical picture ends there, but the conceptual journey continues, flowing naturally into the next theme, the way black holes influence the universe beyond their horizons, how they power jets, shape galaxies, and act as engines driving cosmic evolution. To wander farther into the interior of a black hole is to enter a place where geometry takes on a new kind of meaning, a realm where the familiar structure of space-time folds inward, and the quiet flow of gravity becomes the only guide. Inside the event horizon, inevitability replaces choice, not through force, but through the deep curvature of space-time, a curvature so steep, so complete, that every possible future leads toward the center. Forward in time, and inward in space, become the same direction. This merging of roles, this blending of temporal and spatial meaning, creates one of the most serene conceptual landscapes in all of physics, a place where motion is a continuation of the universe's geometry, and where falling is simply the natural expression of time. As you drift deeper into this inward flow, you might imagine the coordinate grid bending around you, lines of space tilting inward, lines of time pointing toward the singular region, an elegant rearrangement of the axes that shape reality. The experience remains gentle, smooth, free of sensation, because free fall removes weight, cancels pressure and allows the geometry to guide you without resistance. The deeper you fall, the more compressed the radial direction becomes, distances shrinking, curvature intensifying, the inward slope steepening as you descend through spacetime. This shrinking of radial distance is not something you feel physically, but something built into the geometry, a soft narrowing of the universe as the singular region approaches, a funnel contracting in slow, steady gradients. If the black hole is rotating, the interior becomes even more intricate, a swirl of frame dragging, a gentle twist in spacetime that continues beyond the horizon, carrying everything with it, particles, light, observers, all caught in the rotation of the fabric itself. Rotation introduces new shapes, ring-like structures, extended singularities, regions where the inward future is not directed toward a point, but toward a loop of extreme curvature, a structure unique to rotating black holes. But even here, the experience for a falling observer remains smooth. Spacetime simply tilts, twists, and carries you deeper, following the geometry of the Kerr interior, a solution elegant in form, yet incomplete in physical meaning, a mathematical space awaiting quantum insight. This incompleteness softens the concept of the singularity, turning it from a point of infinite destruction into a boundary of knowledge, a place where equations signal their own limits, where new physics must emerge, perhaps replacing the singularity with a finite region, a dense core, a quantum object that resists further collapse. Some theories imagine a bounce, a transition to another region of spacetime, a rebirth of the collapsing matter on the other side of the geometric boundary, a cosmic bridge formed by the mathematics of curved space. Others imagine quantum pressure halting collapse, creating a Planck-scale core where density reaches a maximum, but not infinity, a region beyond which spacetime cannot be compressed further, a quiet resolution of the singularity problem. Still others propose that the interior holds layers of quantum information, encoded in states we do not yet understand, states that preserve details of the matter that fell inward, preventing collapse into true geometric singularity and replacing it with a rich quantum structure. Let this uncertainty drift gently through you, not as confusion, but as possibility, a reminder that the universe still holds mysteries, quiet ones, waiting for discovery. Even without a complete theory, the geometry we do understand paints a peaceful picture, a calm descent through spacetime, guided by curvature, not chaos. The deeper you fall, the more spacetime narrows, until the radial direction becomes too small to describe in classical terms, a soft fading of that coordinate, a quiet approach to the region where theory dissolves into speculation. Time continues, but space becomes limited, the geometry pressing inward in a way that cannot be modeled by familiar physics. And yet, the experience remains free of violence, because violence requires resistance, and there is none in free fall, only the smooth continuation of motion, the gentle unfolding of a geodesic path, the natural expression of the universe's shape. Even tidal forces, often portrayed as catastrophic, depend entirely on the size of the black hole. And for supermassive black holes, these forces near the horizon are minimal, imperceptible, allowing an observer to fall deep inside before curvature differences grow large. This quiet descent, unnoticed at first, becomes a deeper and deeper surrender to the geometry, the narrowing of the inward direction, the increasing tilt of spacetime toward the center. But this narrowing stops being describable at a certain point, and that point marks the boundary of what classical relativity can say, the edge of knowledge, the moment where the singularity awaits, not as a physical object, but as a placeholder, a point where equations fail and where a quantum theory of gravity must take over. This is the true calm at the heart of a black hole, a region not of chaos, but of questions, not of destruction, but of incomplete understanding. A quiet place where physics invites curiosity, and where the limits of our models become a source of wonder. With this quiet interior explored, the journey now rises outward, toward the influence black holes have beyond their horizons, how these silent objects become engines of galaxies, powering jets, regulating star formation, and shaping the universe on enormous scales. A new theme begins to emerge, the outward impact of gravity's deepest wells, and how black holes, despite their silence, become some of the most powerful engines in the cosmos. Black holes, despite their reputation as silent absorbers of light, are among the most powerful engines in the universe, shaping galaxies, driving jets, regulating star formation, and orchestrating vast flows of energy across cosmic distances. Their power does not come from what happens inside the horizon, but from the behavior of matter and fields in the region just outside it, a place where gravity curves spacetime so deeply and shapes motion so strongly. That energy is released with extraordinary efficiency. To understand how black holes act as engines, you must imagine the space around them not as empty, but as dynamic, alive with plasma, magnetic fields, radiation, and the slow spiral of matter falling inward. Accretion disks are the first and most striking feature of these engines, thin, rotating structures of superheated gas, spinning faster and faster as they approach the event horizon, each orbit converting gravitational potential energy into heat, light, and motion. In these disks, temperatures soar to millions of degrees, particles collide at extreme speeds, and magnetic fields twist and reconnect, all driven by the inward pull of curvature, the same gentle geometry that shapes orbits, now guiding matter into luminous spirals. Despite their brightness, the disks themselves remain orderly, thin layers of plasma arranged by angular momentum, each ring moving according to precise physical laws, each orbit reflecting the shape of spacetime. The inner edge of the disk lies at the innermost stable circular orbit, the point where spacetime curves too sharply for stable motion, beyond which matter can no longer circle, and begins its final inward fall. This transition is smooth, a gentle slide inward, accompanied by a last burst of radiation, a final conversion of energy, before the matter disappears beyond the horizon. Because of this process, black holes are some of the most efficient energy engines known, able to convert up to 40% of the infalling matter's rest mass into radiation, far more efficient than nuclear fusion, far more efficient than any engine humanity could build. This efficiency creates luminous structures seen across the universe, quasars, active galactic nuclei, and blazars, all powered by supermassive black holes, all shining with the energy released by accretion. Some of these objects outshine entire galaxies, their light coming not from the black hole itself, but from the spiraling, heating, accelerating matter just outside it. Above and below the accretion disk, magnetic fields wind tightly, twisting into helical structures, channeling plasma into narrow beams that extend far into interstellar space. These relativistic jets, launched from regions near the event horizon, are among the most powerful and focused energy streams in existence, sometimes stretching for thousands or even millions of light years. Inside these jets, particles travel at speeds close to the speed of light, guided by magnetic fields, collided by shock waves, accelerated by electric forces born from rotation and curvature. And yet, despite their power, the jets remain stable, coherent, collimated over vast distances. Structured by the same laws that shape the disk, the same geometry that forms the horizon, the same magnetic fields dragged by rotation, their formation is still one of astrophysics' deepest questions. But a central concept is the extraction of energy from the black hole's spin, a mechanism known as the Blandford-Znajek process, where magnetic fields anchored in the disk tap into the rotational energy of the black hole, pulling power from the twisting of spacetime itself. This process illustrates a subtle truth, that black holes do not merely consume, they can also give, transferring rotational energy outward, driving jets, heating galaxies, shaping cosmic structure. These energy flows influence entire galaxies, regulating star formation by heating gas, preventing it from collapsing too quickly, ensuring that galaxies evolve over billions of years, balance between cooling and heating, between collapse and expansion. Supermassive black holes at galaxy centers orchestrate this balance, not through force, but through energy distribution. Through the radiation and jets produced by accretion, through the gentle but persistent influence of gravity. When a black hole feeds actively, its jets can blow bubbles in the surrounding gas, carving cavities in galaxy clusters, sending ripples of pressure through the intergalactic medium, preventing cold gas from condensing into stars. When it rests, the galaxy cools, new stars begin to form, and the cycle prepares to renew, waiting for the next feeding episode. The next surge of gravitational energy, the next release of light and plasma. This feedback loop is one of the most elegant regulatory systems in the universe, a self-balancing mechanism that keeps galaxies from burning too brightly or collapsing too quickly, a cosmic thermostat controlled by the quiet giants at their centers. Even beyond jets and radiation, black holes shape energy flow through gravitational waves. Ripples in spacetime emitted when two black holes spiral together, merge, and form a single, larger object. These waves carry enormous energy, released in the final moments before merger, traveling across the universe at light speed, stretching and squeezing space itself, whispering the story of the collision to distant detectors. The energy encoded in these waves reveals mass, spin, and details of the space-time geometry around the merging holes, providing some of the clearest insights into strong field gravity and the behavior of curvature under extreme conditions. As you drift deeper into this theme, let your mind settle into the idea that black holes are not merely sinks, not empty voids, but engines, regulators, architects of cosmic motion. Their influence extends from the smallest scales to the largest structures known, guiding energy, shaping gas flows, controlling star formation, coordinating galactic evolution, all through the patient, inevitable, and deeply elegant work of gravity. And now, with this understanding resting gently in your thoughts, the journey begins to drift toward another frontier. The puzzles that challenge our theories, the mysteries that stretch the limits of physics, the paradoxes that arise when quantum laws meet the curvature of space-time. A soft transition begins toward information, entropy, radiation, and the deepest questions black holes invite us to explore. Black holes continue to act as engines long after their initial formation, their influence spreading outward through light, through magnetism, through gravity itself, quietly organizing the structure of galaxies and shaping the evolution of the universe. To drift deeper into this theme, you can imagine the region around an active black hole, a landscape of spiraling plasma, of twisted magnetic fields, of particles accelerating along invisible lines, all powered by the gravitational well at the center. Even the space around the disk becomes energized, heated by radiation, filled with winds of ionized gas, pushed outward by pressure and light, carving vast cavities into the interstellar medium, expelling matter from the galactic core. These winds, though gentle compared to jets, carry enormous amounts of energy, pushing gas outward, regulating the supply of cool material that forms new stars, keeping the galaxy in balance, preventing runaway star formation. This regulation is one of the most important roles black holes play, not as destroyers but as caretakers of galactic ecosystems, ensuring that stars form slowly, steadily, over billions of years, rather than all at once. Without this feedback, galaxies would collapse into bursts of star formation, burning their gas in sudden waves, leaving behind exhausted, silent, dark structures. Instead, supermassive black holes provide gentle, periodic injections of energy, heating the surrounding gas, preventing collapse, maintaining equilibrium. These injections take many forms: jets carving channels through the galactic halo, radiation heating clouds of hydrogen, winds pushing matter outward, shock waves rippling through galaxy clusters. Each of these processes arises not from chaos, but from the geometry around the black hole, from the way space-time shapes motion, from the way magnetic fields guide energy, from the natural behavior of plasma under extreme conditions. As you drift through these ideas, you can imagine the slow, cyclic rhythm of galactic evolution, periods of quiet, followed by gentle bursts of activity, each one regulated by the central black hole, each one shaping the long-term history of the galaxy. This interplay is visible on the scale of galaxy clusters as well, where jets from supermassive black holes carve cavities in the hot intracluster gas, creating bubbles that rise like air pockets in water, lifting material outward, cooling the core, sending waves of pressure flowing through the cluster. These waves, observed as ripples in X-ray images, carry energy across hundreds of thousands of light years, a silent testament to the power of accretion, a sign that a quiet black hole at the center of a galaxy can influence the temperature of gas far beyond its immediate surroundings. Even more subtle effects occur on smaller scales, where black holes shape the orbits of stars, guiding them into stable trajectories, forming star clusters that circle the galactic center, their motion revealing the mass of the invisible object within. These stellar orbits, measured with exquisite precision, confirm the presence of supermassive black holes, their gravitational influence written into the paths of stars, each orbit a signature of the curvature at the core. As you imagine drifting above such a system, you might see stars whipping around the black hole, tracing ellipses that reveal the mass hidden beneath, their motion silent, steady, predictable. The stars feel no pull in the everyday sense. They simply follow the shape of spacetime, the geometry sculpted by the black hole beneath them, moving along curves that reflect the mass at the center. This gravitational architecture extends far into the galaxy, defining rotation curves, setting orbital speeds, stabilizing the galactic disk, and guiding the motion of billions of stars. And yet, despite all this influence, the black hole remains tiny compared to its galaxy, usually less than 0.001% of the total mass, a quiet anchor, small yet essential, holding the structure together. This paradox, small in mass yet enormous in influence, highlights the power of gravity concentrated into a deep well, a reminder that curvature, not size, determines the reach of a black hole's effects. From shaping galaxies, the theme drifts naturally to the cosmic web, the vast network of filaments connecting clusters of galaxies, where supermassive black holes influence the flow of matter, the temperature of intergalactic gas, and the formation of large-scale structures. Across these enormous distances, jets and winds deposit energy, distribute heavy elements, and create pressure differences that shape the filamentary network, a quiet, persistent influence extending far beyond the horizon. As you drift deeper into this picture, you might feel the weight of this cosmic architecture, the slow, patient shaping of the universe, guided by gravity's most concentrated forms, silent engines powering the evolution of galaxies, clusters, and the cosmic web. But black holes also act as engines in another, more subtle way, through the conversion of mass into gravitational waves, ripples that spread across the cosmos, carrying information about their sources and energy drawn from their motion. When two black holes spiral together, their orbits shrink as they radiate gravitational waves, waves that stretch and squeeze space-time, waves that travel billions of light-years, delivering the story of the merger to distant detectors. These waves carry away huge amounts of energy, converted directly from the curvature of space-time, a process made possible only by the extreme geometry near the merging holes, a dynamic dance of gravity, a rhythm played on the fabric of the universe. The final collision, lasting only milliseconds, releases more power than all the stars in the observable universe combined, for that brief moment, and yet the energy passes silently, stretching and compressing space as it travels, imperceptible to humans, but unmistakable to sensitive detectors. These mergers deepen the gravitational well, creating a single, larger black hole, its mass increased, its horizon expanded, its curvature reshaped. The energy emitted in these waves influences the dynamics of galaxies, the distribution of matter, and the behavior of dark matter halos, small effects when considered individually, but significant over cosmic time. Through these many channels, black holes act as engines, transforming gravitational energy, kinetic energy, magnetic energy, and even rotational energy into light, heat, radiation, winds, jets, and waves. Everything flows outward, even from objects defined by their inability to allow escape, illustrating the paradoxical nature of black holes, silent yet powerful, dark yet luminous in their influence, hidden yet essential to the structure of the universe. This completes the quiet exploration of black holes as engines, their role in powering galactic centers, regulating star formation, launching jets, and sending gravitational waves across cosmic distances. And now, with this understanding gently settled, the narrative begins to drift toward one of the deepest mysteries in physics, the strange interplay between quantum mechanics and gravity, Hawking radiation, entropy, information, and the paradoxes that arise when the smallest scales meet the most extreme curvature. A soft transition begins toward the next quiet frontier, the mysteries black holes whisper into the universe. To enter the realm of information, paradox, and mystery is to drift into the deepest questions black holes inspire. Questions that stretch the limits of physics, questions that weave together gravity, quantum mechanics, thermodynamics, and the subtle language of entropy. At the heart of these mysteries lies a simple yet profound question. What happens to information when something falls into a black hole? Information, in the scientific sense, refers to the details of a physical system, the arrangement of particles, the quantum states they occupy, the properties that describe what something is and how it behaves. Quantum mechanics tells us that information cannot be destroyed, that the evolution of any closed system is reversible, its details preserved in subtle ways, even when transformed. But a black hole seems to challenge this principle, because once matter crosses the event horizon, it cannot return, and any information it carries appears to vanish from the observable universe. This tension between relativity and quantum mechanics creates the famous information paradox, a puzzle that has motivated decades of research and continues to shape our understanding of the universe. Let your awareness drift into this paradox, feeling its quiet tension, its soft contradiction, its invitation to deeper thought. To explore it, we begin with one of the gentlest and most surprising ideas in black hole physics: Hawking radiation. In 1974, Stephen Hawking showed that black holes are not perfectly black, but emit a faint thermal glow, arising from quantum effects near the horizon, a glow so soft, so gradual, that a stellar mass black hole would take far longer than the age of the universe to evaporate. This radiation emerges from the quantum vacuum, the restless sea of particle-antiparticle pairs that flicker into existence and then annihilate, even in empty space. Near a black hole's horizon, these pairs can be separated, one falling inward, the other escaping outward, creating the appearance that the black hole emits particles, slowly losing mass over time. This process links black holes to thermodynamics, giving them a temperature and, more surprisingly, an entropy. Entropy, in physics, is a measure of the number of microscopic states consistent with a macroscopic description, a count of how many possible configurations exist for a system, even when those details cannot be seen. Black hole entropy is enormous, proportional not to the volume of the black hole, but to the area of its event horizon. A stunning discovery that hints at something profound, that the information content of a region of space may be stored on its boundary, rather than within it. This idea that volume can be encoded in area lies at the heart of the holographic principle, a concept suggesting that the universe itself may function like a hologram, with the information describing a region encoded on its surface. Let this idea drift gently across your thoughts, space containing information, but boundaries storing it, a quiet trade between volume and area, a soft hint that spacetime may be more subtle than it appears. The holographic principle offers a way to resolve the information paradox, because if information is stored on the horizon, then nothing is truly lost. Even if matter falls inward, the details could remain encoded on the boundary, woven into the surface geometry, preserved through subtle quantum correlations. This perspective softens the paradox, replacing the idea of destruction with the idea of transformation, information hidden but not erased. Another gentle approach emerges from the concept of black hole complementarity, the idea that information can appear to be both reflected at the horizon and pass inward, depending on the observer, without contradiction, because no observer can witness both descriptions simultaneously. This duality, this coexistence of perspectives, is a hallmark of quantum theory, where measurements depend on reference frames, and reality is shaped by the limits of observation. As you drift deeper into these ideas, you may sense that the paradox is not a contradiction in nature, but a sign that our models must be unified, that gravity and quantum mechanics must one day merge into a single framework. Researchers have proposed many potential resolutions, each offering a quiet new angle on the mystery, and each carrying its own kind of elegance. One idea introduces soft hair, subtle quantum fields that linger on the horizon, carrying away information through faint, almost undetectable imprints, ensuring that details are not lost, but slowly radiated outward over time. Another proposal suggests that the event horizon itself may encode information in a fine-grained pattern, woven into the structure of spacetime, a quantum fabric capable of storing unimaginable amounts of detail, far more than any conventional structure could hold. Still another invokes entanglement, the deep quantum connection between particles, suggesting that the interior and exterior of the black hole are linked, that information can be preserved through correlations, even when particles fall inward. Each of these possibilities reveals something about the nature of physics, that information is not simple, that space and time are not rigid, that the universe may store its details in ways we cannot yet fully imagine. Hawking radiation deepens the mystery further, because as the black hole evaporates, it must release all the information it once absorbed, yet the radiation it emits appears thermal, featureless, carrying no visible imprint of its origins. This leads to the question, can the radiation carry information subtly, encoded in correlations, too delicate to see without a complete quantum theory of gravity? Many physicists believe the answer is yes, that the radiation is only apparently thermal, and that the fine structure of the outgoing particles encodes the information lost during collapse, preserving unitarity, the quantum rule that information cannot be destroyed. Let your thoughts rest gently on this possibility. Information carried outward not as patterns of light, but as patterns of correlation, subtle, elusive, but real. These correlations may be so delicate that only a full theory of quantum gravity can reveal them, a theory that unites the geometry of spacetime with the probabilistic structure of quantum mechanics, a theory still unknown, still forming at the edges of human knowledge. As you drift through these concepts, you may sense the quiet poetry beneath them, the idea that the universe remembers, even when details seem lost, that information persists, woven into horizons, encoded in radiation, preserved in the structure of spacetime itself. This understanding leads naturally to black hole entropy, a concept tying the area of the horizon to the number of possible internal states, implying that the horizon is a vast storehouse of information, a two-dimensional surface containing the details of a three-dimensional region. This holographic picture hints at something profound, that space-time may not be fundamental, that it might emerge from deeper quantum processes, from entanglement, from information, from relationships between tiny, hidden degrees of freedom. If space-time emerges from information, then black holes become laboratories, revealing this structure at its most extreme, inviting us to study how information shapes geometry, how entropy shapes horizons, how quantum mechanics shapes gravity. These ideas stretch our imagination, not with violence but with subtle beauty, a quiet rethinking of the universe's foundations. A gentle blending of fields once thought incompatible. The information paradox remains unsolved, yet every proposed resolution reveals something new, something elegant, something that deepens our understanding of both physics and reality. This completes the soft exploration of information, paradox, entropy, radiation, and holography, a journey through the quiet mysteries that black holes place before us. And now, the narrative begins to drift toward the final great frontier, the edge of understanding, where quantum gravity, string theory, and the limits of mathematics converge, a region where certainty fades and curiosity rises, inviting the mind to explore what lies beyond our current horizon of knowledge. As the mind drifts deeper into the mysteries of information and entropy, the quiet frontier ahead becomes clearer, a place where our understanding begins to thin, where equations lose their precision, and where imagination blends with theory. This frontier is the meeting point of quantum mechanics and gravity, a realm where the smallest scales intersect with the most extreme curvature, and where black holes reveal the limits of our knowledge. At this edge, new ideas emerge, softly, tentatively, each proposing a way to unite the quantum world with the geometric language of spacetime. One of the most subtle ideas involves quantum gravity itself, the long-sought theory that would describe the behavior of spacetime at the smallest scales, where distances approach the Planck length, and where the familiar smoothness of geometry dissolves into something granular, something woven from quantum relationships, something not yet fully understood. In this realm, the continuum of spacetime might break down, replaced by discrete units, by loops, by vibrations, or by networks of quantum information, each idea reflecting a different attempt to capture the essence of gravity at its deepest level. Loop quantum gravity suggests that spacetime is made of tiny loops, woven into a vast network, a quantum fabric in which area and volume are quantized, not continuous, each loop carrying a small but finite amount of geometry, a whisper of curvature. If this picture is right, the interior of a black hole could be supported by this quantum structure, preventing collapse to a true singularity, creating instead a finite region where spacetime cannot be compressed further, a quiet core, a point of rest for the collapsing matter. In this view, the singularity is resolved not through new forces, but through the granular structure of spacetime itself, a soft boundary created by quantum geometry, a gentle limit replacing the infinite density predicted by classical relativity. String theory offers a different vision, one where the fundamental constituents of the universe are not particles, but vibrating strings, tiny one-dimensional objects whose modes of vibration correspond to different particles, fields, and forces. In this framework, gravity emerges naturally from the vibrations of closed strings, and spacetime itself becomes part of the deeper quantum structure, not fundamental, but derived, an effect of the ways strings interact, entangle, and organize themselves. Black holes in string theory often possess richer internal structures, not singular points, but extended objects, fuzzballs of quantum information, configurations that fill the region inside the horizon, eliminating the singularity entirely, and storing information in a complex, yet finite form. In this picture, the interior of the black hole is not empty, but full, a dense cloud of strings and brains, each vibrating with quantum information, each contributing to the entropy encoded on the horizon. This fuzzball idea provides one possible resolution to the information paradox, because if black holes are composed of these extended structures, then infalling matter does not disappear into a singularity, but becomes part of a rich quantum configuration, its information preserved in the structure of the fuzzball. Other theories blend geometry and information even more deeply, suggesting that spacetime emerges from entanglement, that the very shape of the universe arises from patterns of quantum connection, that gravity is the manifestation of how information is distributed, arranged, and correlated across space. In this view, the horizon of a black hole becomes a boundary between different patterns of entanglement, a thin surface where information is reorganized, encoded, and preserved even as matter falls inward. These ideas blur the line between geometry and quantum theory, suggesting they are not separate domains but two sides of the same underlying structure, both arising from deeper principles not yet fully understood. Firewalls present another frontier, a proposed solution to the information paradox that challenges our assumptions about the calm nature of the horizon. This idea suggests that the horizon might not be smooth, but could contain a violent region of high-energy particles, a firewall that destroys anything falling inward, breaking the equivalence principle, and contradicting general relativity's prediction of a gentle crossing. The firewall hypothesis arises from attempting to preserve unitarity, the quantum rule that information cannot be destroyed, and it suggests that entanglement between interior and exterior particles must break near the horizon, creating a burst of energy. But this idea remains controversial because it contradicts the smoothness predicted by relativity and because it fractures the foundations of spacetime in ways difficult to reconcile, turning a quiet horizon into a place of disruption, a conclusion many physicists resist. Most researchers continue to search for softer solutions, approaches that preserve the calmness of the horizon while still protecting the principles of quantum mechanics. Approaches that do not force a violent boundary, but instead reveal new structures that maintain harmony between the theories. Some propose that subtle quantum correlations, soft hair, encode information on the horizon, providing a way for details to be preserved, released slowly through Hawking radiation, and preventing the need for firewalls. Others suggest that the interior and exterior of a black hole share a deep form of entanglement, one so strong that the paradox dissolves when seen from the right perspective, revealing that information is never truly lost, but hidden in complex correlations across the horizon. As you drift through these possibilities, you may sense that the edge of understanding is not sharp, but soft, a gradient between what is known and what is guessed, a region where the universe invites creativity, logic, and imagination. At this boundary, mathematics becomes both a guide and a question, showing where our theories succeed and where they begin to fail. Einstein's equations describe the curvature of spacetime beautifully, but they break at singularities, revealing their incompleteness, hinting that a deeper theory must lie beneath. Quantum mechanics governs the small but cannot describe the extreme gravitational fields inside a black hole or the merging of spacetime at the horizon, leaving a gap that must be bridged. The search for quantum gravity is the search for this bridge, a unification of principles, a smooth connection between the geometric and the quantum, between curvature and probability, between the large and the small. Black holes sit at the center of this search, quiet beacons calling us toward deeper understanding, structures that reveal both the power and limitations of our theories, objects that challenge intuition, yet remain serene, silent, and mathematically elegant. As your thoughts rest on this frontier, you may feel the confidence of physics in some places, and its uncertainty in others, a gentle balance between what is known and what remains mysterious. This completes the exploration of the edge of understanding, the quiet meeting point of gravity and quantum theory, the place where black holes reveal the limits of knowledge and invite new ideas to emerge. And now, with the journey approaching its end, the narrative softens, preparing to drift into the epilogue, a final reflection on black holes as quiet architects of the cosmos, and the peaceful return of the listener to rest, carried by the stillness of the universe. At the edge of understanding, where certainty fades into possibility, black holes reveal not only the limits of our theories, but the quiet beauty of the unknown. This region of thought is delicate, a place where physics does not end abruptly, but dissolves gently into questions, each one inviting slower breathing, quieter curiosity, a soft acceptance that the universe is deeper than our current models. To drift here is to walk along the boundary between what we can describe and what we can only imagine, guided by mathematics, by symmetry, by intuition, yet still aware that the path beyond remains hidden. Black holes sit precisely at this boundary, their horizons marking not just physical limits, but intellectual ones, surfaces where classical ideas begin to warp, where quantum rules grow faint, where new principles whisper from beneath the equations. One of the deepest challenges lies in unifying gravity with quantum mechanics, a task that has resisted every attempt at complete resolution, a quiet puzzle that has shaped decades of research, each piece revealing a little more of the picture, but never the entire whole. General relativity describes gravity as curvature, smooth, continuous, geometric. Quantum mechanics describes matter and energy as discrete, probabilistic, granular. At the horizon of a black hole, these two descriptions should meet, blend, and coexist. Yet the theories resist merging, like two melodies in different keys, beautiful in isolation, but dissonant when combined. This mismatch becomes most visible near singularities, where curvature grows without bound, and quantum effects can no longer be ignored, yet no unified theory exists to describe both at once. This is why black holes are more than astronomical objects, they are signposts, pointing directly at the need for a deeper framework, a new theory of nature that integrates geometry and quantization, smoothness and discreteness, the large and the small. Several possible frameworks emerge as candidates, each offering a glimpse of what might lie beyond. String theory proposes that all particles, all forces, all interactions are vibrations of tiny strings, their modes of vibration giving rise to mass, charge, spin, and fields. In this vision, gravity emerges naturally, a product of particular vibrational patterns woven into the quantum tapestry of spacetime. Black holes in string theory sometimes appear not as empty voids, but as fuzzballs, rich, structured, full of quantum degrees of freedom, a vision that replaces the singularity with a cloud of vibrating states, preserving information, eliminating the infinite curvature of classical relativity, and offering a gentle resolution to deep paradoxes. Loop quantum gravity offers a different picture, where spacetime itself is quantized, woven from networks of finite loops, tiny quanta of area and volume, a granular fabric beneath the smooth appearance, a geometry made of discrete building blocks. In this picture, the singularity never forms, because spacetime cannot compress beyond the minimum quantum volume, instead reaching a finite density, a quiet balancing point, a core supported by quantum geometry, hinting that black holes may bounce, expand, or continue into new regions. Both approaches, despite their differences, suggest something profound, that the interior of a black hole is not a place of infinite collapse, but a domain where classical equations stop and new physics begins. Another frontier emerges in the study of firewalls, the proposal that the horizon might not be smooth, but instead marked by an energetic boundary, a region of intense radiation, a wall of quantum disruption. This idea arose from attempts to resolve the information paradox, suggesting that preserving information might require breaking the smoothness of spacetime at the horizon, creating a contradiction with general relativity. If firewalls exist, they would transform the horizon into a place of quantum volatility, a region wherein falling observers encounter energy instead of calm, a conclusion that feels deeply at odds with the serenity predicted by classical physics. And yet, most physicists suspect that the universe prefers harmony, that the horizon remains smooth, and that the paradox resolves through softer, more subtle mechanisms, perhaps through quantum correlations, entanglement, or holographic encoding. These ideas lead naturally to the holographic principle, one of the most elegant proposals in modern physics, suggesting that the universe may fundamentally be two-dimensional, with the third dimension emerging from the structure of information, encoded on surfaces, woven into the boundaries of spacetime. If this principle is correct, then black holes are holograms, their interiors encoded on their horizons, their volume represented by patterns on a surface, their information stored in ways that defy our ordinary intuition. This perspective softens many paradoxes, allowing information to remain accessible, allowing entropy to be understood as surface encoding, allowing gravity to emerge from quantum relationships, shifting our understanding of spacetime towards something richer, stranger, gentler. At this edge of theory, mathematics becomes a lantern, guiding the mind through regions where empirical evidence grows sparse. But logic still illuminates the landscape. Tensor networks, entanglement geometry, ADS-CFT duality all hint at the same idea, that spacetime is not fundamental, but emergent, born from deeper structures, from the pattern of correlations between quantum degrees of freedom, from information itself. If spacetime emerges from entanglement, then black holes become windows into this deeper level, revealing the seams of the universe, the places where information shapes geometry, where gravity and quantum rules intertwine. And yet, despite these beautiful possibilities, much remains unknown, uncertain, quiet. Black holes do not give up their secrets easily. They whisper them through Hawking radiation, through entropy, through gravitational waves, through the delicate geometry of horizons. But they never shout. This final region of exploration, this edge of understanding, is peaceful precisely because it is incomplete, because it invites wonder. Rather than demanding answers, because it allows the listener to drift into curiosity, without urgency, without pressure, without the need for resolution. It is a space where imagination and physics meet, where ideas float freely, where the universe feels vast, open, beautiful. And now, with the frontier gently explored, the narrative begins to settle, preparing to drift into the epilogue, a final reflection on black holes as quiet architects of the cosmos, and a soft return to rest, guided by the calmness of the universe itself. As you continue drifting along the quiet boundary where knowledge fades into possibility, the landscape of theory grows softer, more abstract, yet no less serene, a place where mathematics moves like mist, and the universe invites us to imagine what lies beyond our current reach. This is the final stretch of the intellectual journey, the continuation of the edge of understanding, where questions flow gently into each other, and each idea becomes a stepping stone toward even deeper mysteries. One of the subtle challenges in this region is the nature of spacetime itself, whether it is truly fundamental or whether it emerges from something deeper, a hidden structure composed not of points and distances, but of information, entanglement, or even quantum computation. Several approaches to quantum gravity hint at this emergence, suggesting that the smooth, continuous spacetime described by Einstein may be a large-scale illusion, a macroscopic appearance arising from microscopic patterns, the way temperature arises from molecular motion, or the way a fluid surface appears smooth, despite being made of discrete particles. In this vision, spacetime is not a stage, but a product, a consequence of relationships between deeper entities, entities not yet fully known, but whose collective behavior gives rise to geometry, curvature, and gravitational attraction. This idea is supported by the holographic principle, in which the description of a region of space exists on its boundary, like a projection, a subtle encoding that hints at a deeper origin. If this principle extends throughout the universe, then spacetime itself may be emergent, arising from the way information is arranged, stored, and entangled. Black holes play a central role in this picture because their horizons behave like surfaces of information, storing enormous amounts of entropy, dictating the possible internal states, and organizing the flow of quantum data. Their entropy scales with area, not volume, a clue that the fabric of the universe itself may be two-dimensional at its deepest level, with the third dimension emerging as a kind of hologram, a reflection of deeper rules. Drifting deeper into this possibility, you might imagine the universe as a web of entanglement, each connection pulling spacetime into shape, each correlation giving rise to distance, curvature, and motion. In such a model, a black hole becomes a region where entanglement patterns shift dramatically, where the geometry collapses into dense, intricate regions, and where information is stored with maximal compactness. These patterns may form the true structure of the interior, replacing classical singularities with networks of quantum relationships, creating a space where geometry dissolves into pure information, a quiet lattice holding the memory of everything that has fallen inward. This perspective offers one of the softest resolutions to singularities, not by adding new forces or breaking relativity, but by revealing that spacetime itself is not valid at those scales, that the interior must be described by a different language, a quantum language woven from entanglement. Another frontier appears in the study of soft hair, subtle quantum imprints on the horizon, too faint to detect in classical physics, but capable of storing vast amounts of information, each hair representing a degree of freedom, a slight deformation in the quantum fields around the black hole. These soft hairs hold the promise of preserving information, allowing details of infalling matter to remain encoded at the surface, slowly influencing the Hawking radiation, subtly correcting the thermal spectrum, and ensuring that unitarity is not broken. In this view, the horizon is not smooth, but textured with quantum detail, a living surface rich with information, quietly radiating clues over unimaginable timescales, until the black hole evaporates entirely. This evaporation itself is a remarkable process, one that highlights the need for quantum gravity, because Hawking's original calculation relies on semi-classical physics, quantum fields on a classical background, an approximation that breaks down when the black hole becomes small. As the horizon shrinks, quantum fluctuations in spacetime become stronger, the geometry becomes uncertain, and the radiation becomes sensitive to the precise structure of the quantum state. Eventually, a full quantum theory is required to describe the final moments, to determine whether a remnant remains, whether the black hole disappears entirely, or whether the evaporation reveals new physics, perhaps releasing the last bits of encoded information, perhaps transforming into another structure, perhaps transitioning into a new state of spacetime. These possibilities remain open, quiet invitations for future discovery. Soft suggestions that the universe has more to tell us, more to reveal through careful thought and deeper exploration. Another frontier concerns the geometry of wormholes, tunnels through spacetime predicted by certain solutions to Einstein's equations, tunnels that could connect distant regions or even different universes if they exist, if they can be stabilized, if quantum effects allow them. Recent ideas suggest that wormholes may be linked to entanglement, that two entangled black holes might be connected by a geometric bridge, an Einstein-Rosen wormhole, not traversable, but present as a manifestation of quantum correlation. In this picture, entanglement and geometry become inseparable, two aspects of the same underlying structure, hinting that space itself may be woven from quantum relationships, that connection creates distance, that correlation creates shape. This relationship, known by the phrase ER equals EPR, proposes that wormholes and entanglement are two descriptions of the same thing, a profound and gentle idea that shifts our understanding of both spacetime and quantum mechanics. At this boundary, even time becomes a subtle concept, its flow shaped by gravity, its direction emerging from entropy, its meaning tied to the structure of information. Inside black holes, time and space mix in unusual ways, and at the quantum level, time may behave differently. Perhaps not fundamental, perhaps emergent, perhaps arising from deeper processes in the quantum state of the universe. Such ideas are speculative, yet they carry a quiet beauty, a gentle invitation to think beyond the familiar, to accept that the flow of time may be woven from correlations, from the structure of the wave function, from the growth of entanglement. Mathematics continues to guide this frontier, revealing patterns, symmetries, dualities that connect seemingly distant ideas, each connection offering a new hint, a new doorway into understanding. But with each step forward, the horizon of the unknown expands, revealing more questions, more mysteries, more delicate structures waiting to be understood. This is the nature of the edge, not a hard boundary, but a soft one, a gradient between what we know and what we are learning to imagine, a place where curiosity can drift without end, where the universe feels open, vast, infinite. As the exploration of this final section settles, the narrative begins to slow, preparing to move gently into the epilogue, a closing reflection on the calmness of black holes, the beauty of their mysteries, and the quiet reassurance that the universe, even at its most extreme, remains serene, structured, and full of wonder. As the journey quiets and the long exploration settles into a gentle stillness, the universe seems to lean in softly, as if listening to its own calm breathing. All the ideas we have wandered through, the gravity, the horizons, the information, and the mystery, they begin to weave together, forming a soft tapestry of understanding, a landscape where the mind can rest, even while drifting through the most extreme objects known to physics. Black holes, these quiet monsters that shape the universe, have revealed themselves not as threats, but as teachers, as anchors of structure, as architects of galaxies, and as keepers of the deep symmetry between gravity and quantum mechanics. In their darkness there is order, and in their silence there is a profound clarity. The calm they impose upon spacetime, the steady curvature they create, the gentle way they guide nearby stars, all of it unfolds with a slowness that comforts rather than alarms, a cosmic rhythm measured not in moments, but in millions of years, or billions, or more. As you sink deeper into this closing reflection, let the scale of these structures soften your thoughts, let the enormity loosen the boundaries of your awareness, and let the weightless drift of cosmic time carry you. Because black holes in all their gravity remind us that stillness is a force of its own. That calm can reshape the universe, that silence can guide the motion of stars, and that the unknown can cradle the mind rather than frighten it. The event horizon, the boundary we explored so slowly, is not a wall, not a violent edge, but a quiet threshold, a soft separation between what can be seen and what can only be inferred. Nothing special happens there to the falling traveler. No flash, no barrier, no sudden change in physics, only the steady flow inward, the deepening of curvature, the slow, gentle surrender to gravity's architecture. This understanding alone, that black holes are smoother than imagination suggests, can bring a sense of peace, a reminder that extremes are not always abrupt, that the universe favors continuity, that even its strangest structures obey rules that are soft, mathematical, and beautifully consistent. Beyond the horizon, in that region where classical geometry fails, the softest truth is that we do not know the full story, and that not knowing is part of the wonder, part of the gentle invitation these objects offer. Mystery, when approached without urgency, becomes a place to rest, a quiet field of possibility, a space where curiosity does not seek resolution, only understanding, only a feeling of connection to the deeper structure of reality. Black holes sit at the intersection of gravity and quantum mechanics, and in doing so, they reveal the unity of nature, the hidden coherence that bridges the very large and the very small, the cosmic and the subatomic, the geometric and the probabilistic. They show us that information matters, that entropy shapes the universe, that horizons store memories, and that even evaporation, even disappearance, may preserve the delicate threads of quantum detail. As you drift through these thoughts, let them settle like slow particles in a still pool, each idea descending quietly, each concept finding its natural place until the surface becomes clear again, smooth, reflective, calm. The energy released by black holes, through jets, through accretion disks, through tidal interactions, reminds us that creation and destruction are woven together, not as opposites, but as complementary processes, each shaping the cosmos in balanced ways. Stars are born where gravity gathers material. Galaxies evolve under the influence of massive black holes. Entire clusters respond to their central giants, and across the universe, these silent objects orchestrate growth, regulation, and renewal. In this way, a black hole is not an end, but a beginning, not a void, but a sculptor, not an eraser, but a stabilizer of cosmic structure. And so, as the narrative draws to a close, the universe feels larger, quieter, and more beautifully interconnected. Each horizon a whisper, each curvature a gentle reminder, each photon path a soft curve through spacetime's tapestry. You might imagine now, floating near the calm, immense presence of a supermassive black hole, seeing not a void, but a dark sphere reflecting the glow of orbiting gas, light bending around it in smooth arcs, colors swirling in slow, hypnotic motion. The surrounding stars drift with patient grace, their paths determined by the deep geometry beneath them, each orbit a story written in gravity, each cycle a quiet testimony to the stability of the cosmos. The darkness at the center is not threatening, but restful, like a silent lake at night, absorbing light without disturbance, holding complexity without revealing it, keeping the secrets of matter and energy with infinite composure. And as you drift, the scale widens further. The entire galaxy reveals itself as a spinning system, shaped, steadied, and guided by its central black hole, millions of stars moving together in a slow spiral, each completing orbits that last longer than civilizations, longer than species, longer than memory itself. This sense of time, deep and unhurried, brings the mind into the same calm rhythm, a pace at which thoughts soften, breathing slows, and awareness becomes lighter, more diffuse, more open. Because black holes, in all their extremity, teach patience, teach silence, teach the gentle discipline of letting go. They are cosmic reminders that even the most powerful forces can be expressed with remarkable softness, that the universe does not rush, does not force, does not push, but unfolds naturally, smoothly, with a quiet confidence in its own laws. As you rest within this final reflection, allow the boundaries of thought to dissolve a little, letting the imagination drift through deep space-time, across curved geometry, through horizons, into the soft quantum glow of the unknown. Let yourself feel the unity of the ideas, the way gravity, entropy, information, and geometry all merge into a single, coherent picture. A picture painted not with noise, but with stillness, with structure, with the quiet harmony of physical law. And in that harmony, you may sense a deeper calm, a gentle reassurance that the universe is not chaotic, not hostile, but ordered, balanced, and profoundly beautiful. Even in its darkest places, there is peace. Even in its most mysterious regions, there is structure. And even at the limits of knowledge, there is softness, a quiet invitation to wonder, without urgency, without pressure, without fear. As the exploration ends, the universe remains open, vast, and soothing, a place where each thought can drift freely, each breath can settle, and each moment can unfold with the same slow grace as a star orbiting a black hole. Let the calm linger, let the stillness expand, and let the gentle quiet of the cosmos guide you into rest, where curiosity becomes dream, and the dream becomes silence, soft, deep, infinite.